All right, here we want to look at a couple of characteristics about polynomial functions that are also going to be true, but now we're going to turn our attention specifically to the real zeros of a polynomial function as well as its turning points, and mostly just concern ourselves with kind of possibilities that we could have in terms of the number of real zeros as well as the number of turning points in a graph. So I'm going to bring back this picture that you saw earlier that shows you some polynomial function examples that goes from degree 0 through degree 5. Okay, and what I want you to draw your attention to first of all right here is the turning points in each of these graphs. So remember, when we define turning points, a turning point needs to be a point where the function is going to change from going uphill to downhill or vice versa. So it changes from increasing to decreasing or vice versa, right? So you'll see that this function right here doesn't have any turning points because it never changes from increasing to decreasing. It's actually just constant all the time, right? And then this function right here is always increasing, so it never changes from increasing to decreasing or vice versa. So that has no turning points. This function right here does have one turning point. It's going to happen right there because it goes from decreasing to the left of the point, and then to the right of the point it becomes increasing. So therefore that one has one turning point, right? And then you'll see that this function right here does have two different turning points. And then this function has three turning points. And then the last one does have four turning points, okay? And in all of these graphs, this is actually showing us the most number of turning points that each particular kind of polynomial can actually have. So a degree 5 polynomial will have at most 4 turning points. It would never have 5 or more, okay? So like the number of turning points at the most always is going to be one less than the degree. But there's just a little bit more to the story there that you want to understand. And that's the fact that, okay, so here we've got a couple of degree 3 polynomials, right? So the number of turning points has to be at most 2, right? Now, it turns out that it can't just be like 0 or 1 or 2, like all of the numbers less than 3 in terms of possibilities. It turns out that it could have 2, so exactly 1 less than the degree, but it would be impossible for it to have 1 turning point. So basically what that means is if it's an odd degree, it has to have then just an even number of turning points possible. So since the only even numbers less than 3 are 2 and 0, then having 2 or 0 turning points are the only possibilities for cubic functions, right? And that one doesn't have any turning points because it goes from decreasing to decreasing, right? And then just so you can kind of see another flavor of this right here, these are 3 examples of polynomials that are all of degree 6. So therefore the number of turning points that it can have must be an odd number because it's an even degree polynomial. And then it has to just then be less. So the only odd numbers that are less than 6 are 5, 3, and 1. So having exactly 1 turning point, or having exactly 3 turning points, or having exactly 5 different turning points are the only possible number of turning points that can happen for an even degree polynomial of degree 6 then, right? So just in regards to the number of turning points, right, that if you have an odd degree polynomial, then it's going to have an even number of turning points. And then if you have an even degree polynomial, then we know that it's going to have an odd number of turning points, right? So that's always going to be true. And then also the most number of turning points for a degree n polynomial is going to be n minus 1, right? So the number of turning points that it has that's the most always has to be one number less than the highest exponent, right? But it doesn't always have that maximum, right? It just needs to be like multiples of 2 decreasing from there, right? So that gives us information about the turning points, okay? And then the other characteristic we're going to look at in this little section right here is talking about the real zeros. So remember that a zero of a function is going to be the x value or values that make the y value equal 0. Okay? So if they're real zeros, then they must correspond to being x-intercepts on the graph. Okay? So in all of these graphs, I've actually given examples of graphs where each kind of type of polynomial shows the most number of real zeros it can actually have. So you'll see that this one right here, it doesn't have any zeros. It's a constant function. I guess there are some constant functions. Only one that if it's on the x-axis, it has like a lot of zeros, right? But that was kind of a special case. The rest of these are all kind of just like more normal in that a linear function that's diagonal can have at most one real zero because it only has one x-intercept. This one has two x-intercepts. This one has three. This one has four. And then this one has 5 different ones, right? And that actually gives you the most number of real zeros. So the number of x-intercepts that a polynomial function could have is going to match up with exactly the degree of the polynomial, right? So just note that, like right here, here's 3 cubic functions. So there's going to be some y equals x to the third plus whatever, like equation that can make each of these 3 graphs, right? Just know that, like, okay, it could have 3 different x-intercepts, right? But then it could have 2 or it could have 1, okay? Odd degree polynomials actually always do have to cross the x-axis at one point, so it would be impossible for a cubic to actually have no x-intercepts. But just know that when we have even degree polynomials, with some of those, they might not have x-intercepts. So like if you had like a graph that goes like this or something, right? It's going to have to be even degree because the ends go in the same way, and clearly it has no x-intercepts, okay? So like if this was like a y equals x to the 4th plus whatever equation, it could have no x-intercepts, but then it could have exactly 1, or it could have exactly 2, or 3 or 4 different ones, okay? So it's the odd exponent ones where you're going to be guaranteed that it has at least one real root. Okay? So in terms of the number of real zeros in the graph of a polynomial function, just know that the odd degree ones, they always have at least one real zero. Okay, so they all can't just be imaginary. And then the even degree ones, they could be all imaginary to being like all real matching up with the degree. So there's a little bit more possibilities there with the even degree ones, right? And then just in general, that for a degree n polynomial, it can have at most n different or distinct real zeros at most, right? So that's the maximum number of zeros. So if the highest exponent is n, then n is the number of distinct real zeros that it can have at a maximum. Okay? So applying that just a little bit right here, we're asked to determine the possible number of turning points as well as the maximum number of real zeros for each polynomial function. Okay? So for this function right here, we've got f of x equals 4x to the 8th plus 9x to the 5th minus 2x squared. So in terms of the number of turning points, that is always going to be 1 less than the degree, and then even numbers from there. So like, because f right here has a leading term of 4x to the 8th, that means that f is a degree 8 polynomial, right? So therefore the number of turning points that this function could have could be 7, 5, 3, or 1. It's got to be an odd number, right? So the most that it could have is 7. We don't really know without like actually graphing the graph, you know, how many turning points it might actually have, but we just know that it's going to either have 7 or 5 or 3 or 1. Okay? And then in terms of the maximum number of real zeros, because the degree of this polynomial is 8, it can have at most 8 distinct real zeros. Okay, so then it might have 7 or 6, 5, 4, 3, 2, 1, and it could also possibly have no real zeros as well because it's got an even degree. But we're just asked for the maximum, so at most 8. So for this one right here, the number of turning points that it could have, because of the degree, is going to be 5. That's the highest exponent. Then it could have either 4, because that's 1 less, or 2, or 0, none turning points. Okay, so those are the possibilities for the number of turning points it could have. And then for the real zeros that it could have exactly 5 at the most. Okay, because it's an odd degree polynomial, right, that's guaranteed to have at least one real zero. So the number of distinct real zeros this function g could have then would be just 1, 2, 3, 4, or 5.